So yesterday, in last week class, we were talking about permeability. So today's class, we are going to see how to find out the permeability using constant head test and falling head test or variable head test. So if you remember, I have mentioned that your constant head test is suitable for coarse grain soils. If you remember, C for C, I said. So for coarse grain soils, we use constant head test, and for fine grain soil, we use variable or uh, falling head test. So constant head test. So as the name indicates, the head is maintained constant. Okay, so at a constant uh, head, you can see here you have a overhead tank. Okay, this is what we call it as a overhead tank. So from the overhead tank, you have your sample. So to the sample, the water will be permeating. So in the overhead tank, there is a continuous supply of water, and it will have a outlet at a particular head. So beyond this head, if the water rises up, the water will be coming out through this overflow. Here you can see, okay, if beyond this head, if the water comes out, the water will be coming out, and there will be a constant supply of water as the water comes out in this exit. Okay, so head is the, as I said, the free water surface level between uh, two, where you are going to, I said, only if you have head difference, there is going to be a flow of water. When you are going to keep both the head at the same, there will be no flow of water. So this is the height from the tank at this point to the exit at this point, that is your through the soil. Okay, so this height we measure and we call that as h. Okay, so we need a permeator mold. Your permeator mold has standard dimensions. So through the permeator mold, the water is going to flow, and we are going to collect water. What we are going to do? We are going to collect water in a jar. Okay. So as I mentioned, in a constant head test, we are going to collect water. We are for a particular time. For example, for 1 minute, 2 minute, 3 minute. Okay, for different time, at least some five different time intervals, we are going to collect water. So for a imagine if it is going to be fine grained soil like clay or something, the water will be coming in drops. So at 1 minute or 2 minute, the water you are going to collect is going to be very very less. Okay, some one drop or two drop. That's why this test is suitable only for coarse grain soil, because in coarse grain soil only the water flow will be very high, and you'll be able to collect at least some amount of water or a particular discharge amount of water at a particular time. That is why your constant head test is suitable only for coarse grain soil. So you have burette connections here. You have burettes. Okay, so we'll be connecting this overhead tank to the permeating mold. Inside your permeating mold, your soil will be compacted and placed at a particular density. You have to saturate the soil before allowing permeability, because if you remember Darcy's law, it is valid only for a saturated soil condition. So we are going to saturate the soil for 24 hours at least, and then we will be the next day we will be starting the test. So place the permeator mold assembly at the bottom of the tank. So you have to attain a steady flow. So once you start open the outlet of the mold, you shouldn't start your test. You have to allow some time to water to flow through the soil, and it should attain some constant flow condition. Okay, that will take some short time. Okay, so then you have to start your test. So you have to put your soil in your permeation mold, then you have to connect it to the overhead tank. Then you have to remove if there is going to be any air bubbles or anything. So allow sufficient time of water to flow and saturate the soil, and remove entrapped air inside, or else they will be keeping it in a bucket of water to saturate it. Okay, it depends. So determine what is the head, diameter of the mold, and height of the sample. That details we need. We need to know what is the head at which it is going to flow, what is the diameter of the sample, and what is the height of the sample. So the calculation part is very easy. This formula QL equal to QL by AHT. The coefficient of permeability K equal to QL by AHT. So Q is the discharge that you are collecting. For example, some 15 ml, 20 ml, 30 ml. Okay, that where 1 ml is going to be 1 cc. Then L is the length of the mold. For example, it can be some 10 centimeter length. Area of cross section, that depends on the diameter of the sample. Then constant head at which you are going to measure. You have to measure this height. I told you have to measure this height through a scale or something. You have to measure the tape. You have to measure what is the height, that is a head causing the flow. Then you have to note down what is the time. So as I said, you keep a beaker at the bottom of the outlet from the sample. You open the wall, then you have to allow it to flow for any particular time. For example, for every 30 seconds they are collecting. So you have seen that the amount of water collected is going to be 36 ml at first trial and 37 ml at second trial. We can do some 3 to 4 trials. The head is going to be 20 centimeter from the top. So then you directly we have to substitute the values. Then we get what is the permeability. You can see that the permeability is around 10 power minus 5 meter per second. If it is going to be clay, okay, if it is going to be clay soil, this will be around 10 power minus 9, minus 8 something, which is going to be very very low. Okay, so that's why we cannot conduct falling head test, sorry, constant head test for your clay soil. Fine. So it's a direct substitution. Whatever the we have to note down what is the time taken, what is the length of the sample, what is the head causing the flow, how much water we are collecting, and area of the sample. That gives you the permeability in meter per second. Next is going to be your variable head method or falling head. So in this method, your head is not going to be constant. So the head is going to be keep on changing. Okay. So in a variable head method, you can see that. One second. So I have shown you a burette here. So you have to find out what is the time taken for the water to flow from this height to this height. For example, if this is 90, if it is going to be 80, you are going to find out what is the height, what is the time taken for the water to flow from this height to this height. I'm talking about variable head test. Okay, that's what the picture shown here. So here, if you see the formula to find out the permeability, it's going to be little lengthy but not a complex formula, very easy. Okay, so K equal to 2.303 AL by AT log base 10 H1 by H2. That is the formula. So once we know what is the formula, we have to see, okay, what are the parameters we are going to find out. So this small a is the area of the standpipe. So this we call it as a standpipe or a burette. You have to note down what is the diameter of this burette, and that area you have to find pi d square by 4 h, pi d square by 4. That will give you the area. Okay, it's area of the standpipe. Then this capital L is nothing but the length of the sample, the length of the sample. Then capital A is the area of cross section of your sample. So we know what is the diameter of the sample, so we know what is the area of cross section. Then time taken. So we are going to, what we are going to do while in the test. So we are going to note down the time taken for the head to for the head to come from H1 to H2. What is the time taken? So this is your first head. So this is your in this case, okay, so this is your outlet of your pipe. Okay, so this is the head at which it is flowing. So this is head H1 and this is going to be H2. Free reservoir, that we call it as a free reservoir, which we consider as a head. Okay, for the open to atmosphere, it should be open to atmosphere. That's why we take either the exit, or in this case, here is where the reservoir, you can see this is where the water is open to atmosphere. That is why they have taken that as H. In some cases it will be immediately below the soil. Okay, so that's why we call that as head. Okay, so from H0 to H1 we are going to note down what is the time taken. You have to understand one more thing is when the water flows through the soil, it is going to lose energy. That is a head loss, actually, you can tell. Okay, that is also one more way of telling the head loss. So when the water flows from this to this end, the water is going to lose its energy. Whatever energy it has at this point, it will be lost to some amount, and it will be reached at this. So when the water flows from this to this, it will have the same energy. The energy will not change. Okay, so that's why in some books they will give the free reservoir as a head, or in some books they give us this point as a head, but it's not going to make any difference. So we are going to find out the time taken. You can see here. So your initial head is at 450. uh, the time taken for it to reach to 46.5 centimeter is going to be 120 seconds. So directly we are going to substitute in the formula, and we get what is the coefficient of permeability. So again, why falling head method is not suitable for your coarse grained soil. Okay, so in coarse grained soil, if you are going to conduct falling head, you know that the water is going to flow at a very fast rate. So from 50 to 46.5 or any value, it will commit in a 1 second or within a fraction of second, I can tell. Okay, so within 1 or 2 seconds it will come very, it is flowing at a very faster rate. So that's why your falling head test is not suitable for coarse grained soil. uh, Here we are no, the water will be flowing at a very slower rate. Once you open the wall, the water will be coming in drops. So water will be coming in drops. So you will be noting down what is the time taken for the head to come from 50 to 46.5. Okay, so when we directly substitute 2.303 AL, area of the standpipe. This is the area of the standpipe through which it is flows. L is the length of the sample, area of the sample, time taken for the head to come from H1 to H2. We will do some 2 to 3, 3 trials. Some book will be, or some material may show this formula. Here if you note down, this is ln. So to remove this ln only, we are actually putting as 2.303 times of log. So we can report your permeability either in centimeter per second or meter per second. If you see here, you can see that it is around -7 meter per second, or it even come to -9 meter per second value. Fine. So we started with compaction, then we moved to permeability, which is one of the engineering property. uh, then comes the shear strength. Okay, so as far as permeability is concerned, we have seen constant head method and falling head method. There is one more way to find out the permeability, that is from your consolidation test. When we do one dimensional consolidation test, we can find out the permeability indirectly from that test also. The other important parameter of soil is going to be shear strength. Okay, whenever we design any structure on for the soil, we always be concerned what could be the shear strength of the soil, whether it is going to be your bearing capacity or anything. Okay, which is directly connected to the shear strength of the soil. Okay, so we know that all your failure in soil is going to be a shear failure. We call that as a shear failure. That is, the particles, if you see this, the particles will slide over one another, because soil is going to be a particulate matter. Okay, so the soil will be sliding one over one another, and it is going to cause you a shear failure. So any failure is soil is going to be a shear failure, for which shear strength is going to be an important parameter whenever you are going to concern about the strength of the soil in terms of bearing capacity for the footing and everything. Okay, so in soil, in order to find out the shear strength, okay, uh, that is, here we put it as S, or we put it as tau. Okay, this is also the standard notation. Okay, so tau equal to c plus sigma tan phi. Very very important formula. Okay, even though we have many advanced coming out. Okay, this is the first and very basic formula to find out the shear strength of soil, which was given by Moore Coulomb. More has found one part, and then Coulomb has added to that. So we call this as a Moore Coulomb equation. Tau we call that as tau equal to C plus sigma tan phi. Okay, when it is going to be a pure cohesive soil, if you're going to consider the soil as going to be pure cohesive soil, then you won't be having this part. This is your phi will be going to be 0. So we call this your tau. The shear strength will be directly um connected with your C value, that is your coefficient. That's why if you remember in a bearing capacity equation, uh, those who know can just relate it to it. If you remember your bearing capacity equation for a clay soil, it is going to be just 9 NCU. Okay, uh, 9 times of N into Cu. Okay, so your where it is going to be pure clay soil, where your other terms of like N5 and NC, 9 NCCU. Okay, we put as 9 NCC. So if your bearing capacity is directly related to the cohesion only. So when you are going to have a pure cohesive soil, whether if you are going when if you are going to have a pure sandy soil, okay, we call this as, this term will be 0, so you'll have only this term. So tau is equal to sigma tan phi. Tau is equal to sigma tan phi. So that is when you are going to have a pure cohesionless soil. Okay, so if you see this graph is between sigma and tau. Okay, so it's where this is your sigma and this is going to be your tau. Okay, between normal stress and shear stress, uh, when you're going to have phi 0, you'll have only the coefficient factor, and when you have C0, you'll have a line. So with the angle of that line is going to give you your angle of internal friction. So phi we call that as angle of internal friction, and C we call it as cohesion. These are the two factors which is going to be contributing to the shear strength. C and phi. C and phi. They are the very important terms, or important you can say your main line of your soil mechanics, C and phi. Okay, so C is cohesion, phi is angle of internal friction. So why do we actually have this sigma part, that's your normal stress? In general, if your angle your cohesionless soil, the phi can be influenced by this normal stress, whereas your C will not be influenced. That's why we have this sigma with the phi term. Okay, fine. So it's tau equal to C plus sigma tan phi. Your tau is nothing but the shear strength of the soil. C is the cohesion intercept. Sigma at pressure normal to the shearing plane, and phi is the angle of angle of shearing resistance, or angle of internal friction. Anything you can tell. Fine. So the another one thing in soil mechanics is going to be effective stress. So effective stress is nothing but your total stress minus pore water pressure. That is, if you take if you take a soil, okay, this is one soil particle and this is going to be one soil particle. At the point of contact, there is going to be a stress. That is what we call it as effective stress. Okay, so your soil will be transferring, if you have a load applied, okay, your soil will be transferring this load through this point of contact. Okay, so that stress at the point of contact, we call that as effective stress between the grains. uh, this effective stress is what matters than the total stress. Okay, in soil mechanics we never worry about what is the total stress. We always consider this effective stress, because it is going to be the pore water pressure is going to be expelled. What is this pore water pressure again? So in between the voids, so if you have your particles, okay, so you have void here. Okay, so in between the voids, if you are going to have water, once when you apply a load, okay, initially the all the stress will be taken by the water. Okay, so you the particles won't be contributing. So once if you have a drainage, okay, once if you have a drainage, the pressure will be built up. Once you load it in the water, if it is going to take the load, the pressure will be built up, and this pressure will be expelled if you are going to allow a drainage, or else this pressure will be kept on building. So if you remember, there is Tersagi spring analogy. We call it as very useful for to understand this effective stress concept. So we have a spring, Tersagi spring analogy. So when and this is you have a beaker and it is filled with water. Okay. So when you apply a load, this spring is similar. This spring is modeled as the soil particle, and this is your water in the pores. When you load it, the spring will not come down. Okay, so all the load that you are transferred will be going to the water and it will be built up as a pressure. When you allow a drainage, the water will be coming out, and your spring will be coming down. So the slowly the effective stress, particles will be taking the load, and all your water will be coming out. So all the load will be carried by the particles alone once you have the entire water is drained. Okay, so this effective stress is a very very important parameter. Whenever we do any formulation or anything, we are worried about what's the effective stress. In consolidation everywhere, the effective stress plays an important role. So your effective stress is nothing but total stress minus pore water pressure. So in your shear strength equation, if you are conducting, whether you are allowing your water to drain out from the soil, or if you are not allowing the water to drain out from your soil, the behavior is going to be very much different. Okay, so that is why they have formulated in terms of total stress and effective stress equations. For a soil, if it has water inside and if you are loading it, pore water pressure will be built up. Okay, so the behavior of the soil or the strength of the soil in that condition will be very less. The same soil, when you are allowing water to drain from it, when you are providing drainage from it, for it, when you are loading it, then the strength of the soil will be obviously very high when we consider the previous case. That's why we always worry about water to be drained out from the soil. Okay, always we worry about the drainage conditions of a particular place. So we shouldn't allow water to either enter, either you shouldn't allow to enter, or we should allow it to escape from the soil. Why this why this effective stress is very important is, see, if you remember, there is a condition in field that we call it as quicksand condition. Okay, we call it as quicksand condition, uh, that where you have seen in movies and everywhere, you will be pulled inside. It's actually it's not something like it is pulled inside. Okay, it is quicksand condition is something where your pore water pressure will be very high. Okay, and it will become equal to your I mean your total stress, and your effective stress will become zero. That is, your effective stress is becoming zero. So when your effective stress is zero, what does it mean? There is no point of contact between the particles. So all your particles point of contacts will be broken, and it is like it is going to be very thick slurry kind of thing. Okay, there is a upward seepage of water. Mostly in that condition is that issue of quicksand will occur. Okay, so there will be upward seepage of water, and there will be effective stress will become zero, and you end up it in quicksand condition. So, and also sometimes in piping failure everywhere in dams. Okay, all this is related to this pore water pressure. Very very, you can say, like a danger. Okay, you shouldn't allow pore water pressure to build up. So if you are allowing pore water pressure to build up, then it will obviously going to reduce the soil strength. Even in case of earthquakes, if you see in earthquakes, when there is going to be earthquake, you have seen that there are conditions like sand boiling and liquefaction. We call that as liquefaction, similar to a quicksand condition, where your pore water pressure will be rapidly built up, and your soil will lose its strength, and the effective stress will become zero in a liquefied condition. So the soil will flow like a liquid. Okay, your soil will be flowing like a liquid, and all your structure may fall. So that's why this effective stress we have to be very much concerned, and we have to be always see that our pore water pressure is negligible. Okay, fine. So, what are the general methods to find out this shear strength? That is, in lab, we have direct shear, triaxial, unconfined compression test, and laboratory vein shear test. Okay, so these are the methods to find out. The direct shear and triaxial, they we generally classify into three main groups. One is UU test, unconsolidated undrained, consolidated undrained, and consolidated drained. All these tests are based on drainage. That is the first thing you have to remember. Okay, so uh, whether you are allowing the water to escape from the soil or not, that is what the basic uh, function that is running behind all these types of tests. For triaxial, if you just to remember what is happening in that test, then you won't be ever confused what is this CU, or CD test. Okay, so what is basically whether you are allowing water to come out from the soil, whether you are allowing water to escape or not, that is what going to determine what type of test or what condition it is going to fall. So these they replicate this field phenomena actually. Okay, in field, especially when you are going to have a earthen embankment, where there, whether there when there is going to be a sudden drawdown or anything. Okay, that comes under CU or UU test. It can be CU or UU test. Okay. I'll talk about what is that. Then we'll come out and we can relate it to the field conditions. That's why triaxial is a very very important test. If you want to get a realistic field, if you want to simulate your field conditions in lab, then your triaxial is a very basic. Very important test to be done. Fine. Okay. So as I said, there are two stages in your testing. Okay, stage 1, stage 2. So what is consolidation? First of all, that we have to understand. See, compaction, if you remember, you are removing the air voids or you are reducing the air voids, I can tell in that manner. You are reducing the air voids and you are increasing the density. Whereas in consolidation, you are going to apply a static load. Okay, it is not a dynamic load. You are going to apply a static load, and when you apply a static load, okay, so we have a field or ground condition. Okay, you are applying a load. Okay, so you have your soil here, you have a soil here. So when you are going to apply load uh, on a fully saturated clay soil, okay, so there I sorry. So this is the original height of the soil. Okay, when you apply load, so it is going to decrease in thickness. So this is going to be the final height. So this is going to be a delta H. This we call it as settlement. So the water from the pores will be expelled. Okay, the water from the pores will be expelled and the soil will decrease in thickness. This is what consolidation is. Okay, so in consolidation, you are applying load. So when you apply load, you are allowing for drainage. So the water is coming out. So as water comes out, the soil be the soil will decrease in its thickness and it will attain a constant height. Okay, for the applied load. When you again increase the load, it will again decrease. It's not like it is going to come into a thin section. Okay, there is a constant void ratio. Beyond that, you cannot decrease the void ratio. Okay, beyond that, you cannot decrease the thickness. So when you are going to apply a static load on a fully saturated soil, there is a decrease in height because of the drainage of water. That is what we call it as consolidation. Okay, so stage 1, stage 2. Stage 1 we call it as a consolidation stage, and stage 2 we call it as a shearing stage. Okay, shearing stage means where you are making the sample to fail, where you are going to apply excess load and we are going to make the sample to fail. So in the I'll first go with these three. Okay, in unconsolidated undrained. Okay, that means that unconsolidated means you are not allowing the water to escape. That's why it is not consolidating. Okay, unconsolidated. Undrained means again you are not allowing water. So the first term refers to the consolidation stage, and the second term refers to the shearing stage. So when you have a sample, you apply cell pressure. throughout the sample you are applying the cell pressure. I can show you the picture here. It's okay. Okay, here. So this is your sample. Okay, this is your sample with rubber membrane enclosed and O-rings placed. We have porous stones at the bottom, and this is your loading. Okay, first stage. During the first stage, you won't be applying any load. It is just a piston placed. Okay, you are not applying any load. You are applying a cell pressure. You have a cell here. This is acrylic cell. You apply water. Okay, so with the help of water, you are applying a cell pressure. So when you are applying a cell pressure all around, there is a drainage valve at the bottom. You can see here. So through the drainage valve, if you are allowing or opening the drainage valve, the water inside the sample will be coming out. There is a decrease in thickness. This we call it as consolidation stage. Okay. Now if you are applying a load, once the consolidation is over, when you are applying a load, that we call it as a shearing stage. Okay, once you are applying a load here, you can see here. Okay, so back to the table. So you have to understand the difference between these three. So in your unconsolidated and undrained, both in consolidation stage and shearing stage, you are not allowing the water to escape. Next comes consolidated undrained. Okay, unconsolidated, I mean CU, consolidated undrained. So in your first stage, during applying cell pressure, the in and around pressure we call it as cell pressure. Okay, imagine it's like water press, just compressing the sample. Okay, water is compressing the sample all around. So when the water is compressing it, water is the if you are allowing a drainage, the soil will consolidate. Then when you do the loading from the top, you are applying loading. Okay, cell pressure also there. Additionally, you are applying loading. When you are applying loading, you are closing the valve. You are not allowing the water to come out. Okay, the so because of that, pore pressure will be built up. So then the sample is failed. In the shearing stage, you will be applying. You will be keep on increasing your load, and you will see at which point your sample is failing. Sample failing means it can be a bulging of the sample will happen. Okay, so that we call it as a CU test. Then is going to be CD, where your your drainage valve is open both during the first stage and the second stage. Okay, uh, there is one more uh, impossible test I can tell. You cannot conduct that test. That is going to be your unconsolidated drained test. This is an impossible test that you cannot conduct. That means you are not allowing the drainage in your consolidation stage, and then you are allowing drainage in your shearing stage. That means if you are doing that, what will happen? The sample will automatically consolidate during your drainage stage, during the second shearing stage. Okay, so this is something like an impossible to conduct. Unconsolidated drained test is something impossible to conduct in your triaxial test. So unconfined compression test, UCC we call that as. This we in this we will not allow. Similarly, it is not conducted in a triaxial setup. It is conducted in another loading frame. But this is similar to your UU test we call. It's like similar to your UU test, where you are not allowing the drainage and your loading will be rapidly applied. So this unconfined compression test is similar to your UU test, but these three are only triaxial. These three are only conducted in triaxial, where this is conducted separately. Okay, so you are fine. That is your. I hope there's some message. What is that message? What is back pressure? Okay, fine. So, yeah, yeah. Hmm. In triaxial, or even there is one more permeability I can say, that's called as flexible wall permeability. Okay, similar in which we conduct in triaxial setup kind of. So in triaxial, when we are going to conduct the test for clay soil, we have to ensure that it is 100% saturated. Okay, So what we do is, even though you keep the soil in water or 24 hours or whatever, your clay will not be 100% saturated. You will be able to attain only some 95% or 90, approximately 95% degree of saturation. Okay, so in order to fully saturate the sample, we are going to apply water through the top and through the bottom. Okay, we are going to apply water, or we are going to send the water through the top and bottom at a particular pressure. Okay, we'll have some head difference. For example, the top pressure will be at top will give us some pressure of 290. Okay, and at bottom will give a pressure of 295. So what happens, your bottom pressure is more than your top pressure, so water will try to flow inside your soil. So even if there is going to be some minute pores where you are not able to saturate in ordinary conditions, by applying a very high pressure through the bottom, okay, the water will be able to fill some smallest pores of the soil, clay soil. So this way you will be able to attain at least 98 to 99% of saturation. It is like 100% saturation is a very it's like very uh, highly impossible 100% saturation in clay soil. Okay, so that's what they say. So you can attain 99% up to 99% of saturation, where you are applying pressure through the bottom of the sample, and you are maintaining some pressure difference at the bottom and the top, so that water is trying to fill the pores. Okay, so that's what we call it as back pressure line, or we generally call it as a back pressure line or a volume change line. Okay, so here they have a pore pressure. Pore pressure is something, they will be connecting a transducer or a sensor, where you can measure what is the pore pressure being built up in the soil. Okay, that you can do that. Okay, generally back pressure is nothing but you are applying a pressurized water to flow into the soil, so that the soil is fully saturated. Here they have connected through the top, sometimes it will be connected through the bottom. Okay, so this is actually more effective than through the top. Okay, it depends on different testing conditions. Okay, so fine. Okay, so your fine the angle of internal friction is going to depend on various factors, like particle shape, gradation. As I said, gradation means whether it is going to be a well graded soil or poorly graded soil, a different size of particles present in different percentage, and its relative density. Okay, so again, there are factors affecting the shear strength in clay. Adsorbed water plays a very important role. That's why in clay soil, sand is a free draining material. Okay, even though if pore water pressure builds up, you can easily remove that excess pore water pressure from the sandy soil. But whereas in clay, it is very difficult to remove the pore water pressure built up, and also the clay is also will subject to swelling process by absorbing the water. So your various possible effects of adsorbed water, compressibility, neutral stress, and low permeability provide the clays with almost unlimited variations in shear strength. Okay, so even though if you provide proper drainage and everything, clay soil is a little bit challenging, to find out its I mean, yes, you can find out. There are, that means there are a lot of factors influencing the shear strength of clay soil. That's what I want to tell. Okay, so rate of loading. Soil always, the rate of loading is very 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 important. The rate of loading that you are choosing, if you are loading rapidly, okay, if you are load you are increasing rapidly for the same soil of same property, and there is one more specimen where your loading is slow, okay, rate of loading is slow, then you have a very huge difference in the strength. Okay, so rate of load application is very very important, where when you are going to do a consolidation drained, unconsolidation undrained, that is what here rate of loading comes in. So if you see UU test, unconsolidated undrained test, we call that as a quick test. Okay, it is called as quick test. That is, you no need to wait for your pore water pressure to escape. That is, you are no need to wait for your water to drain. You are closing the valves in both the shearing and consolidation stages, so your test will get over in a day. Okay, you can just place a sample, connect all the sharing and loading connections, and you can start the test. Then apply stage wise, you have to apply load or a pressure. You don't need to wait. Okay, we call this as a quick test. There is one more where you have a CD test. It is the longest or a very time taking test. Okay, so this is a quick test. It finishes in a short duration. Your CD means first you have to apply one pressure, you have to consolidate it. It's not like your water comes out from the soil immediately. Okay, so it takes lot of time. Then you are applying a your what is that, shear. Okay, then again you have to wait. You have to wait for longer time for the water to drain out when you are applying the shear loading. So this is the longest. CD test is useful when we want to know the long term behavior of soil. That's what it means. When you want to know at long term what could be the strength of the soil, then CD test will be performed. At it, as quick test, you is like immediately want to know what could be as a rough idea. You want to know what could be the shear strength of the soil. Okay, so that we can do the UU test. So CU is not something intermediate between these two. This may take some 1 week. This may take some uh, half a day. So this will take some 2 days or something. Okay, so for conducting CD test, we have to take some 1 or 2 weeks. It's a long term test. Fine. So as I said, your rate of loading is going to influence the strength of the soil. Next comes the direct shear test. Okay. So direct shear test, it has many advantages and disadvantages. It is mostly suitable for your coarse grain soil. Okay. For fine grain soil, it is very rare they do a direct shear test. But even then, we can conduct a direct shear test on a clay soil also with additional provisions. So it is more suitably whenever we be in lab, we can see that our direct shear test will be conducted mostly to the sandy soil. So your direct shear test, you have a box. I can show this. Okay, you have a shear box, top box and bottom. They are movable. Okay, and you have some screws which can fix this boxes together. Then okay, these are the screws. Then we have a plates. Okay, we have some drainage plates and these plate another strip plates. Then we have our loading cap. Okay, these are the minimum set, and then we will be placing it in the bigger test setup. Okay, so this is your direct shear test setup, and this is going to be your direct shear box. Okay, so what we are going to do in direct shear test, you are going to fill this box, put the screw. Okay, and you are going to fill this box with the sand in 3 layers in a required density at which you are aiming at to conduct the test. Then you are going to place it in the machine. Okay, in the setup, and you are going to apply load. So this horizontal load here, this will push the box. So because of this load applied, your both the boxes will be moving sideways, and until the soil fails, you'll have a resistance develop. Once the soil fails, the resistance will be overcome and the soil failing will be happening. So basically here what we are going to do, we are sharing the sample. This is what horizontal force is, what we call it as a shear load. Okay, so this is compression load. Compression load means where you are going to apply towards the sample. This is your compression force. and this is your tensile force where we have pulled the sample one against each other. Whereas in shear loading, we are going to push the sample over one over other. So at the point of contact, at this point you'll be measuring, actually this is where we are going to measure the resistance. uh, uh, from this we will be able to find out what could be the angle of internal friction of the soil, granular soil. Generally we take cs 0 in this case. Okay, so you have a box of 6 by 6 size, and you have a place your soil sample here, and you are going to, your plane of failure is predetermined. I told you this is what you call it as plane of failure. So your plane of failure is going to be horizontal. This is where your soil is going to fail. That is one disadvantage of your direct shear test. If you see a clay soil, clay will always have a 45-degree failure plane. Okay, when you conduct a test, when we conduct a test in a UCC, okay, you can see exactly your soil will be sliding over one another. These two pieces will slide over one another at a 45-degree angle. Okay, whereas here your failure plane is fixed at here, this point, which is not going to be the actual failure plane. That is one disadvantage. Okay, so you are what are the three reading we are going to measure? You can see this is your vertical displacement, this is your horizontal displacement, and this is your horizontal load. We are going to measure three parameters. Okay, so when you apply load, the box is going to move. So at horizontal displacement, at what, how much the box has moved, okay, that we measure using your horizontal displacement gauge. And this is your proving ring, which will tell you how much load is applied. And this is going to be your vertical displacement ring, because you are going to put a load here. You can see this is your normal stress or normal stress, okay, which is reflected here. So we know what is a normal stress, how much you are going to apply. At this normal stress, you are going to find out what is going to be the shear stress. And because of during the failure, you will have a vertical displacement also, your soil will also compress little. Okay, so you will be measuring what is this vertical displacement. So three things: one, vertical displacement; horizontal displacement. Your box is moving, you have to know how much it has moved. Okay, and this is your proving ring, and this is your normal load. These four things is what matters in this test. Okay, these slides are explaining what I have to said now. Okay, fine. So I told you we are going to measure horizontal divisions. So each trial you have to change your specimen. You cannot conduct the you cannot conduct the test with the same specimen. Okay, once the specimen has failed, you have to go for the another specimen. So first you are going to fix your normal stress. Okay, so you know what is the density, moisture, size of the specimen, area of the specimen, volume, least count of the strain dial, vertical dial, and your proving ring. I said move three rings, three gauges were there. So you have to note down what is the least count of them, and then uh, you are seeing that it has moved 30 divisions. You have to note down the reading for every 30 seconds. Okay, then you have to note down for every 30 seconds what is the reading. At one point, what will happen? The shear load will be keep on increasing. So as the test starts, the shear load will be keep on increasing. At one point, it will fail. That means it will come down. Once the soil specimen is failed, the shear loads comes down. Then you can terminate the test. Okay, this is your first for one normal stress. So for one normal stress that we are applying, we will be getting one shear load. That is a maximum load. So we'll note down what is the horizontal division. 30 divisions it has moved in mm. 30 into least count. Your least count is going to be zero point zero 0.01. So 30 into 0.01, zero 0.3 mm. So the horizontal movement is going to be zero point 0.3 mm. Then your stress dial, you can see that it is 15. Your proving ring has given a 15 divisions, has moved 15 divisions at a particular time. So you multiply it into a proving ring constant, you will be getting what is the then you have to divide it with your area of the specimen. Okay, so shear load, we are getting shear load. Shear stress is nothing, you will get shear load. Okay, your shear load is going to be this value 15 into proving ring 0.462. Then you are finding shear stress. Stress is nothing but load by area. Okay, so your shear stress is going to be this load divided by the area. Area is going to be 36. Then vertical reading is 1, and that into least count will give you the axial deformation. Okay, so you'll be getting one for one applied, they are applying one normal stress. For example, if it is going to be around 50 kPa. Okay, you are applying a normal stress of 50 kPa, and you are getting a maximum shear stress is going to be around some 10 kPa or something. Okay, so this is for one. You have to conduct three trials, then only you will be able to get your plot. So your plot is nothing but this one is very important, where you are going to find out your phi value. So you will be plotting normal stress versus shear stress for first trial, second trial, third trial. You will get 3 points. You have to connect all the 3 points and measure what is the angle phi. That is how we get our angle of internal friction. Okay, so first trial you apply a normal stress, you apply a loading, your shear box will be moving until it provides a resistance, your shear load will be increasing. Once a sample fails, your shear load will be coming down. So you have to know down what is the maximum shear load that has applied. Then you divide it with your area. So shear stress by normal stress will give you 1 point. Then you have to remove the sample, put a new sample, then again repeat the stress at a different normal stress. If you conduct for 50, then conduct it for 100. So this is in kilogram per centimeter square, I'm talking in kPa. Okay, it's just difference in unit. Okay, so next normal stress you apply for a different normal stress, you do that, conduct the test, find out what is the shear load, then again apply for the third. Okay, at least three trials we have to do. Connect it with a straight line in a graph, normal graph, you get it your phi value. Okay, then this is going to be horizontal deformation versus shear stress. This gives you an idea about how the behavior of the soil is there. Okay, so at different normal stress you can plot what is your horizontal deformation. You have measured it already, you have measured it, and you have plotted for your shear stress. So you can see that how your mean soil has behaved until its failure. Okay, generally we tell that for um, loose sand your failure plane will be like this, and for a dense sand you have a pronounced peak. Okay, so this kind of behavior we find out only from this graph. Okay, so you can see that how the soil has undergone the failure. Okay, how its failure pattern is there. So horizontal deformation versus shear stress, we can plot it. So same thing, I have put it in a clear graph. So normal stress versus shear stress, you conduct different trials and you connect the most you have to connect the points which lies maximum points which lies in the same line. You can see this point is out of the line, you have to leave it. Okay, you have to connect the points which lies in the same line, and you measure what is the angle, you will be able to know, or slope of the line, you will be able to know what is the phi. And this is going to be a horizontal displacement versus shear stress. Fine. Okay, so we are clear with direct shear test. So your direct shear test, it's a quick test again. It is a easy test to do, and it will give you the phi value directly. And for clay soil also we can perform the test. We have to give some drainage plates, and you have to conduct the test with the escaping of pore water pressure and everything. Generally, it is conducted for undrained, so cohesionless soil. Next one is going to be your UCC test. Okay. So unconfined compression test, we call that as unconfined compression test. uh, this is a very important test for your clay soil. Okay, so for clay soil, if we need to find out what could be the shear strength, okay, we can use we do this test. So we are going to apply a compressive load. We are not going to do a shear load, we are going to do a compressive load. Then we are going to find out what could be the shear strength from the test. Okay, so you have a frame here, you can see you have prepared your sample. Length equal to 2 times the dia, that is the what code first. Okay, so the length of the sample should be twice the dia. You are going to place the sample. This is going to be a loading proving ring, and this is going to measure the vertical displacement of the plate. So this plate will be moving in this direction, and that manner you are going to apply a compressive load. And here you can see that the compressive load will be increasing up to a particular point. Then once a sample fails, it will start decreasing. So you have to note down what is the movement of this plate also at a rate of, and you have to note down what is the rate of strain. Okay, so you are going to get your axial load, and you are going to divide it with your corrected area. So what is this corrected area? So you can see that the plate is moving it in upward direction. So the length of the sample will be keep on changing. Okay, the length of the sample is not constant. So we will be doing a correction for that. So that is called as corrected area, for which A naught divided by 1 minus epsilon. 1 minus epsilon will be able to get from your this gauge strain. Okay, what is the strain? Fine. So the specimen setup, record the zero readings, apply the compressive load. You have to take the reading until the proving ring pointer moves in opposite direction. Okay, so that means your load is keep on increasing. You have to note down your proving ring reading and also your vertical displacement reading for any specified type. For every see, there are two ways to do. Either for every 50 divisions of your plate movement, we can note down what is the proving ring reading, or for every time, for every 30 seconds you have to note down what is the horizontal displacement and proving ring reading. Both the ways you can get your answer. Okay, so the readings are taken until the proving ring pointer moves in opposite direction. Sketch the mode of failure and remove the specimen. You have to measure what is the water content. So it is a easy graph actually. So you are finding what is the length of the sample, what is the diameter of the sample, and noting down what is the initial area. Okay, then you are finding out what is the deformation. As I said, here they have noted down for every 30 divisions what is the load. Okay, for every 30 divisions movement in your this gauge, for every 30 division, what is the load? This gauge will be rotating. Okay, so this will be moving, this plate will be moving up, so this will be pressed and this will be moving. So for every 30 divisions you are noting down what is the load in the proving ring. Okay, that will be converted into kilonewton, multiplying with the factor. Then you are finding what is the strain, change in length by original length. Okay, that will be given by your deformation. From this is your change in length divided by original length. Then you finding out what is the corrected area and your stress. So you can see a model calculation. So 3.9 kilogram, that is what for example, that is a reading noted down into your you are finding it into newtons. Okay, in terms of newtons, this kilogram is from after putting your proving ring. Okay, proving ring will give you only the divisions, so you have to multiply with your constant, with your ring constant. Then you will be noting down what is the load. You are converting that into newton by multiplying with 9.81. Your strain percentage, 0.3 by 76. You can see I told you this is a movement. So delta h by l, delta l by l, that will give you the strain percentage. Your corrected area is nothing but a naught by 1 minus strain percentage. So this value. So this is in percentage. So 0.0039 will give you the corrected area. This load divided by corrected area will give you the stress. Okay. So you will be able to plot a graph. Axial strain versus axial stress. You can see that it is keep on increasing, then it will decrease. So this peak is what is your maximum compressive strength of the soil. So we'll be able to find out what is the maximum compressive strength. We can find out what is the shear strength of the soil. So your shear strength is nothing but QU by 2. It's an important gate question in many times I have seen. So from your compressive strength, you can get your shear strength, that is going to be QU by 2. So how is that means? You can see this is a graph between your normal stress and shear stress. So this point is going to be your maximum stress that you have obtained. For example, 102. Okay, you got this point. What is this point is always zero, because that is your confining stress. You can see here in your unconfined compressive strength, there is no confining stress. This is going to be zero. So this stress is going to be 0, sigma 3. Your minor principal stress is 0. So there is no confining stress. So you will be able to get sigma 3 0, and this is sigma 1f. You can draw a neat Mohr circle. Okay, so and this is nothing but your Cu. That is your tau equal to Cu we tell. Okay, for a pure clay soil. So your shear strength is nothing but your undrained coefficient. So this value is going to be Cu. That's why we tell tau equal to Cu equal to Qu by 2. Your unconfined compressive strength, when we divide it with 2, you get your shear strength or the undrained cohesion. Undrained cohesion. Why it is called undrained means you are not allowing any drainage. Okay, you are just preparing the sample, keeping it, and your rate of loading is such that you are not allowing any drainage to happen. So it is your undrained cohesion that we get in our UCC test. Fine. So next we'll move on to your triaxial. So triaxial, as I said, we can very well you can bring your field phenomena, field scenario in the lab by changing the drainage condition. See, if you are going to construct a building in a place, if you know that the initial the construction phase is going to be how much time it is going to take. Okay, we are not sure about how to do a construction. For example, in a clay soil, if you are going to allow the pore water to build up slowly and dissipate it, then we are able to get a good strength. We have to allow the settlement in the construction stage itself. So if you want to know how rapidly we have to construct or how slowly we have to construct, that we can get an idea from our triaxial shear strength. Because if the construction phase is going to be in such a manner that the pore water pressure is able to build up and dissipate, then we have no problem. If the pore water pressure is not dissipated, and if the rapid construction is happening, then at one point, as I told you, your effective stress will going to be decreased to a very less number. Okay, so UU, CU, and CD, these are the three possible drainage path during your before and that is your three possible tests in your triaxial test. It is the most important and somewhat complicated test. I don't see it is a complicated test. It takes time. Okay, it takes some time. Then we can the sample preparation and the connections, everything. It takes a little bit time. Other than it is very, it's going to be very easy test. So it is simulates the field condition among the other tests for determining your shear parameters, that is going to be C and phi. Okay, so you have your test setup. Okay, you are going to place porous stones at the bottom. Place your sample, put a porous stone at the top, put a loading cap and connect to your pedestal, and you have to enclose it in a rubber membrane. Okay, So generally we go for 35 mm I mean 35 mm to 70 mm. 70 mm will be the length, and 35 mm sorry 70 mm dia sample. 70 mm dia, yeah, 70 mm dia if I'm not wrong. Okay. There are some standard rubber membrane sizes are available. Okay. So 70 mm dia we generally go for it. So uh, you have to apply your confining stress through the sides, and you have to allow for drainage if it is a CU or CD. Then you have to apply your loading. Okay, then you have to apply your loading, and you have to see just like other tests. You have to see the load will be increasing up to a particular point, and then it will start to decrease after it fails. So generally it will be the sample will be bulging. So fit the top cell properly. Take care to fit the loading ram at the top and allow water into the cell. So we have to fill the water. This is your cell. We call this as a cell. You have to fill the cell with the water. Okay, the loading is set at 1.25 mm per minute. Okay, the rate of loading. Reading of stress and strain dials are taken at regular interval. Okay, fine. So UU test. In this type, the sample specimens are tested within three or four different lateral pressure without allowing volume change in the sample. So volume change. Why they call it as a volume change? I told you consolidation. When the consolidation is happening, what is that happening? This thickness is decreasing. So this generally we keep the area as constant, where area into length is what is your volume, correct? So we keep the area constant. This diameter is going to be constant. So what is that changing? Only your height is changing, your length of the sample thickness is changing. So that we call delta H. We relate it to the delta V, volume change. Okay, that's why we call that as volume change. If there is no drainage, if there is no drainage means there is no change in the volume. Okay, so that's why they call it as no volume change. The volume change and pore pressure valves are closed throughout the test. Perfect undrained coefficient for saturated condition gives predominantly Cu value. Perfect undrained condition at saturated, that is very important. When you are going to do the test, you have to make sure that your soil is fully saturated. That's why we apply a back pressure, as in discussion thing. Okay, so we have to apply back pressure, and we have to make sure it's saturated, and we'll get a Cu value. And generally in this test your phi will be 0. The angle of internal friction is going to be 0. So this is the curve that we get. Okay, so if your soil is not saturated, for example, properly saturated means what happens is this curve failure envelope will be little bit curved. Okay, so until it will be something like this, and then it will attain a constant. Okay, until you get a saturation, this curve will not be perfectly horizontal. So for a UU test, this failure envelope is perfectly horizontal. This is one important thing. In UU test, your phi is 0, and your your failure envelope is perfectly horizontal. In CU test, that is your consolidated undrained, the specimen is consolidated by giving a lateral pressure. It's a if you see some videos and dig deeper into triaxial, it's actually a very interesting test. You and it's not something complicated. You have your sample. Okay, you have your sample like this. Okay, you are applying lateral pressure. So all around you are applying lateral pressure. That is going to be your minor principal stress, and you are applying water to come out. That is going to consolidate the sample. Okay, and then you have to check with your pore pressure transducer whether the pore pressure for the applied pressure, the pore pressure is dissipated. Then you have to close the drainage. Then you have to apply a load. Okay, so once you apply a load, all around already you have a minor principal stress, that is going to be sigma 3. Now you are applying a load. Okay, then because of this applied load, the sample is going to fail. So at this top plane alone, you will have a major principal stress. So you are applying a load that is which is nothing but delta D. We call this as delta D. So your my major principal stress is sigma 3 plus delta D. That's what we call. Already you have a sigma 3 here. You are applying another load here. So this why this plane becomes a major principal plane. This is called as minor principal plane. Uh, so you are applying a major principal stress at the top, minor principal stress is around. Okay. So because of that, the sample we call this as deviated stress in another term. Okay, deviated stress. So you are applying simply load. Load is applied at the top, and the sample will be failed. Consolidated drained. So you are providing drainage valve is kept open throughout the test. Okay. Um, see you. Okay. uh, if you want to remember in a easy manner, you have to put a something table like this. For gate I used to do that. Okay, fine. So this is the first stage, second stage. UU, drainage valve is closed, drainage valve is closed. CU, drainage valve is open, shearing stage, drainage valve is closed. CD, drainage valve is open, open. Okay, simple, easily you can remember in this manner. Okay. All the complexities is connected to the drainage. Okay, whether you are applying a water to allow whether the water is allowed to escape or not during the. And you have to remember one thing: for the applied pressure only, that water will escape. It doesn't mean the water is completely drained out from the sample. Okay, when you're applying some pressure for 100 kPa, imagine you're applying a pressure of 100 kPa. So inside there will be water, and the pore water pressure will be built up, and water will be coming out. Okay, sample will compress, still water is there. Okay, once you increase the stress to 200 kPa or something, you have to see where you have to wait, still water will come out. Okay, it doesn't mean that when you apply some 100 kPa, all the entire water in the sample is out of it. Okay, so for the water pressure, the water corresponding to that applied load only will be escaping out from the soil. Okay, I hope I am clear with that. I'll just go to the